Good day everyone, I'm Dr. Cello and let's discuss about dehydration. Today we'll delve into the critical role of dehydration in tissue processing, particularly focusing on the use of dehydrating agents. Understanding this process is essential for anyone involved in histopathology or tissue analysis. Tissue processing is a meticulous procedure that involves multiple steps before we can embed the specimen in paraffin wax. This sequence is crucial for preserving the cellular structure and ensuring accurate analysis. Each step builds upon the last, ultimately leading to a high-quality tissue sample. After fixation and decalcification, which is the two vital initial steps, the next phase is dehydration as the third step. This step is essential as it prepares the tissue for the embedding process. During dehydration, we remove both intracellular and extracellular water from the specimen. This is a crucial step because excess water can interfere with the embedding medium and affect the integrity of the sample. Dehydration is not just about removing water, it's fundamentally about ensuring proper wax impregnation. If the tissue is not adequately dehydrated, the wax may not penetrate effectively, leading to poor quality sections that can compromise diagnostic accuracy. Properly dehydrated samples allow for optimal infiltration of the embedding medium, which is critical for subsequent slicing and examination. Let us define dehydration. Again, dehydration is the process of removing water from tissue before the embedding stage. This step is essential for achieving high-quality tissue sample. Dehydration plays a key role in preventing tissue distortion. It helps maintain the structural integrity of the tissue and is vital for ensuring that the cellular architecture remains intact, which is crucial for accurate diagnosis. To effectively remove water, we use specific solutions known as dehydrating agents. These agents facilitate the process of dehydration, ensuring that the tissue is adequately prepared for subsequent embedding in wax. The choice of dehydrating agent can significantly impact the quality and the final sample. So what are dehydrating agents? These are solutions which are used to replace water in tissues with organic solvents. Common dehydrating agents include alcohols such as your methanol, ethanol, isopropanol, and butanol. Next is acetone and dioxane. These agents are used in increasing strengths to ensure effective dehydration while preventing tissue damage. Proper use of these solvents is crucial for maintaining the integrity of tissue samples. Now let us discuss the difference between dehydrating and drying, and it lies in their purpose and process. Dehydrating refers to the removal of water or other solvents from a substance, typically using chemical agents in controlled conditions. In histology, dehydration is done using alcohol or solvents like tetrahydrofuran to replace water in tissue samples before embedding. Drying, this is a broader term that refers to the removal of moisture from a material, usually by evaporation. Drying can happen naturally or through applied heat. Drying can cause significant tissue shrinkage and distortion. Effects of dehydration. Dehydrating agents are strong organic solvents that can lead to shrinkage and extraction of cellular components from tissues. To minimize potential damage during the dehydration process, we should use a graded series of dehydrating agents. Why? This allows for a gradual transition, reducing shock to the tissues. Next is limit exposure time. Keeping the tissue in any dehydrating agent for too long can exacerbate shrinkage and loss of components. And next is gradually replace water. This helps avoid osmotic stress. What do you mean by osmotic stress? When there is an imbalance in concentration of solute inside and outside of the cell, it affects the movement of water in a cell membrane through osmosis. So, water moves from low concentration of solute to high concentration of solute. So, if there is osmotic stress, it can further compromise the tissue integrity. Characteristics of an ideal dehydrating solution. A dehydrating solution should dehydrate rapidly, removes water efficiently without causing significant tissue shrinkage or distortion. It should have a moderate evaporation rate and should not evaporate too quickly or allow controlled dehydration. Also, it should work on fatty tissues. It should be effective in removing water from fatty specimens and should avoid excessive hardening of the tissue. It should not make the tissues too rigid or brittle. Also, dehydrating solution should preserve stains. It should not interfere with the staining procedure, and it should be safe. It should not be toxic or harmful to the body, and it should not be flammable and should not pose a fire hazard in the working environment. General guidelines for dehydration. There should be an adequate volume. The volume of the dehydrating agent should be at least 10 times the volume of the tissue. That's to ensure complete penetration of the tissue. Next is minimize dehydration time. Prolonged exposure may lead to loss of cellular constituents. Use the shortest effective time to prevent tissue damage. Selection criteria for dehydrating agents. Dehydrating agents must be water miscible and anhydrous. It should preserve tissue proteins and not interfere with later processing and must be compatible with subsequent processing fluids. Cost effectiveness can be consideration in laboratory settings. What are the commonly used dehydrating agents? The most common is alcohol. It is used in graded concentrations to prevent tissue damage. Next is acetone. It is fast-acting but highly volatile. Next is dioxane. It is miscible with alcohol, xylene, and paraffin, reducing the need for separate clearing steps. Next is Cellusolve or your ethylene glycol monoethyl ether. It produces less tissue shrinkage but toxic with prolonged exposure. Next is triethyl phosphate. It is non-volatile and less tissue hardening. Next is tetrahydrofuran. It is the universal solvent that dehydrates and clears tissue simultaneously. Alcohol as dehydrating agent. Ethyl alcohol or ethanol is the best for routine dehydration. It is fast-acting and mixes well with water and solvents. Penetrates tissue easily and is safe and affordable. Next is methyl alcohol. It is toxic but mainly used for blood smears and tissue films. Next is butyl alcohol. It is slow-acting, producing less shrinkage, and is used for plant and animal tissues. Dehydration process can start with 70% ethanol, then increase to 95% and 100%. Delicate tissues such as embryos may start at 30% ethanol, and avoid direct transfer from water to absolute ethanol to prevent shrinkage and distortion of tissues. Storage and handling. Tissues can be stored in 70% ethanol but not for long periods. It preserves tissue morphology without causing rapid dehydration, and prolonged period storage can compromise tissue quality. Next is avoid 80% or greater than 80% ethanol for too long periods. Why? Extended exposure to concentrations above 80 can cause tissue hardening. High concentrations can over-dehydrate tissues, leading to rigidity and potential damage. Use 2 changes of 100% ethanol at least 30 minutes each to ensure complete dehydration. Why? These steps ensure that all water is replaced, preventing incomplete dehydration and preserving tissue structure. Next is do not exceed 2 hours in 95% or 100% ethanol to prevent over-hardening of the tissue. What you can see in the slide is the sequence of dehydration for specimens of less than or equal to 4 millimeters thick. First is 70% ethanol in 15 minutes. Second is 90% ethanol for 15 minutes. Third is 100% ethanol for 15 minutes. Fourth is 100% ethanol for 15 minutes. Fifth is 100% ethanol for 30 minutes. And the last is 100% ethanol for 45 minutes. Factors affecting dehydration. A temperature of 37 degrees Celsius helps to speed up the dehydration process, especially for urgent biopsies. Copper sulfate is added as a drying agent. A 1/4 inch layer of anhydrous copper sulfate is placed at the bottom to absorb extra water. When the crystals turn blue, it means that they are fully saturated with ethanol. Ethanol replacement is essential. Once saturated, the use of ethanol is discarded and replaced with a fresh solution to ensure the complete dehydration process. Let us discuss now the alcohol-based dehydrating agents, starting with ethanol or ethyl alcohol, with a boiling point of 78.3 degrees Celsius. Advantages of ethanol. Ethanol is fast, reliable, and effective, and is the best dehydrating agent. Ethanol is non-toxic and miscible with water. It produces minimal shrinkage when used in graded solutions. It is safe for delicate samples such as eyes and embryos. It is inexpensive and is widely available. However, in prolonged use, it can cause shrinkage and hardening. It removes certain dyes and extracts more lipids than acetone. It has a limited miscibility with most resins. Next is butanol or butyl alcohol with a boiling point of 117.7 degrees Celsius. Butanol is a good option when we want to minimize shrinkage and hardening. It's great for slow processing and can mix with paraffin. However, it has a strong odor, works slowly, and requires long infiltration times. Next is tertiary butanol or butyl alcohol, boiling point of 82.8 degrees Celsius. Tertiary butanol is unique because it acts as both dehydrating and clearing agent, also known as universal solvent. It mixes well with several solvents, making it useful for multiple steps, but it is more expensive and has a strong odor and solidifies between 25 degrees Celsius, making handling difficult. Next is isopropanol or isopropyl alcohol with a boiling point of 82.3 degrees Celsius. Isopropanol is a good substitute for ethanol because it has fewer restrictions and causes less shrinkage. It's also more affordable. However, it can't be used in siloidine technique or for staining solutions as dyes don't dissolve in it. Next is pentanol or amyl alcohol with a boiling point of 128 degrees Celsius. Pentanol can dissolve paraffin wax and is miscible with some solvents, such as your 90% alcohol, toluene, and xylene. But it is toxic and requires proper ventilation and does not mix with water, which limits its application. Next is acetone with a boiling point of 56 degrees Celsius. Acetone is a rapid dehydrating agent. It is less expensive than ethanol, and it does not extract dyes from stain sections. It may cause less shrinkage and is non-reactive with osmium tetroxide. However, it requires a large volume, 20 times the tissue sample, and a graded series with xylene before embedding. It needs good ventilation due to rapid evaporation and high flammability. Also, absolute acetone absorbs water easily, risking the incomplete dehydration. And some acids such as uranyl acetate, phosphotungstic acid requires dilute acetone. Next is dioxane or diethylene dioxide with a refractive index of 1.42 and boiling point of 101.5 degrees Celsius. This is an example of a time schedule for dehydration with dioxane in Graupner's method. So you can look at this for reference. Weisberger's method for tissue dehydration. A tissue is wrapped in gauze and suspended in a bottle with dioxane and anhydrous calcium oxide. Dioxane replaces water, which is absorbed by calcium oxide, and the dehydration usually takes 3 to 24 hours. Tissues fixed with chromate fixatives in Rigaud's or Muller's fluid must be rinsed thoroughly with tap water to remove chromate before using dioxane. Dioxane is also a universal solvent as it mixes well with water, alcohol, xylene, and paraffin. It is gentle on tissue over long periods and dehydrates faster than ethanol. However, it requires large volumes and is about 4 times as costly as absolute alcohol. It must be used in well-ventilated areas due to cumulative toxicity and odor. It can distort tissue cavities and needs large volume for dehydration. Next is Cellusolve or ethylene glycol monoethyl ether with a boiling point of 156.4 degrees Celsius. Cellusolve is a rapid dehydrating agent. Tissues may remain in it for months, and it avoids distortion and does not require graded dilutions. However, it is expensive and rapidly absorbs water from the air and requires clearing agent. Next is triethyl phosphate with a boiling point of 215 degrees Celsius. Triethyl phosphate is suitable for routine paraffin techniques, readily displaces water with minimal tissue distortion, and does not excessively harden tissue. It can be used in the staining dehydration sequence and soluble in a range of organic solvents such as alcohol, benzene, toluene, xylene, ether chloroform. It has no disadvantages. And lastly is your tetrahydrofuran. Tetrahydrofuran is fully miscible with water and many organic solvents. It has rapid action with minimal tissue shrinkage or hardening. It has low toxicity and reduced fire explosion risk, produces better results than most universal solvents, and compatible with mounting media. However, it has a strong odor, used in well-ventilated areas, and evaporates quickly. Dyes are not soluble in tetrahydrofuran. For the additives used in dehydrating agents, we have phenol. When 4% phenol is added to each of the 95% ethanol baths as part of the hydration process, it acts as a softener for hard tissue such as tendon, nail, or dense fibrous tissue. In addition, hard tissues can be immersed in glycerol alcohol mixture or in Molliflex. So that is all for the dehydration lecture. Thank you.